Want to reach Mars in just a couple of weeks? Or maybe travel to other stars? Then you'll need to get your hands on some antimatter. And preferably a lot of it. Antimatter engines or antimatter propulsion often appear in science fiction, but is it really just fiction? More than once on my channel I've talked about interstellar travel and different types of engines proposed for it. Reaching other stars is no easy task. Some even consider it impossible, given all the challenges involved. And the low speed of modern spacecraft is far from the only challenge, though it is the main one. The Voyager 1 spacecraft is currently moving away from the Sun at a speed of about 17 kilometers per second. It may seem like the speed of over 38,000 miles per hour is a lot, but as many of you probably know, in the scale of the galaxy, it is nothing. And if Voyager were heading towards Proxima Centauri, the closest star to the Sun, it would take it 74,000 years to reach it. In the context of missions to other stars, we talk about speed in fractions of the speed of light, and Voyager's speed is about 0.00006 of the speed of light. It would be better to accelerate to a more significant fraction of the speed of light. Among the proposed options I've already talked about photon engines, light sails, and so on, as well as nuclear pulse engines and even warp drives. All these types of propulsion can be placed on a sort of a spectrum. Let's say light sails, in one of their configurations, using light from a star or lasers, seem quite realistic. Here, there is no need for fundamentally new technologies. There have already been some working prototypes, even in space, that demonstrated the fundamental viability of the technology. In theory, with a large amount of resources, it would be possible to launch a probe to another star in the not-so-distant future using this method. On the other end of the spectrum, we have warp drives, which warp space-time itself. No matter what some articles on the internet may tell you about NASA developing a warp drive, we are not likely to see their use in the next hundreds of years, if we see it at all. I discussed this in more detail in a separate video. Sure, physics does not rule out the possibility that such a trick with space warping could work, but whether we'll be able to pull it off, very doubtful. Antimatter propulsion on this spectrum could probably be placed somewhere in the middle. More precisely, given that there are several types of engines that involve antimatter in one way or another, some of them are more realistic while others would be closer to warp drives. That's what we're going to talk about today. How can antimatter be used for space travel? What are the types of engines and what are they capable of? Are there any existing developments? When can we see their application? And what are the barriers on the way to this? There are many interesting nuances and details, and that's what we'll discuss today. I'm Andrei, and this is Cosmos Elementary. In my video about photon drives, I briefly touched on the topic of antimatter drives, but this subject is of course much deeper. The idea of using antimatter for propulsion in space in one form or another has been discussed for several decades. You can find a lot of interesting information about this in the scientific literature. Space agencies, including NASA, are also interested in this issue. For example, here's an article from the Jet Propulsion Laboratory which talks about antimatter engines. It considers a scenario with a deliberately very ambitious goal: creating an engine capable of accelerating a spacecraft to 50% of the speed of light, which in theory would allow reaching the nearest stars in relatively reasonable timeframes. And three promising technologies are mentioned here that are most likely to achieve this goal: a light sail powered by a laser, a ramjet based on nuclear fusion, and a matter-antimatter annihilation drive. But half of the speed of light is truly a very optimistic goal. And this paper includes estimates of what needs to be done to achieve it. And to put it mildly, it's still closer to science fiction. But we will talk about this in more detail later. But what's interesting is that antimatter can be used not only to try to reach other stars, It's also quite possible to travel around solar system with such engines. But let's first revisit some basic concepts. Today there are two main, most mature space propulsion technologies that are already widely used on spacecraft. First, of course, there are chemical rocket engines, and second, electric drives. I've also already talked about them in detail in a separate video. What unites them is that both technologies propel the spacecraft using the same principle, which is described by Newton's third law of motion, the law of conservation of momentum, action, reaction, and all that. In short, we expel matter in one direction, and this causes the spacecraft to move in the opposite direction. How fast we can accelerate a spacecraft depends on how quickly the substance, the propellant, is ejected, as well as how much of that propellant is expelled. And this is where the differences between chemical and electric engines begin. In chemical engines, the expelled material is accelerated by chemical reactions. Roughly speaking, the fuel burns, the material is accelerated. The energy for acceleration is contained within the fuel itself. Electric propulsion systems come in different types. For example, in ion thrusters, the propellant is ionized and accelerated by electric fields. And in this case, the energy for acceleration doesn't come from the expelled material itself, but from a separate energy source. For example, solar panels or a radioisotope thermoelectric generator. Chemical engines have a relatively low exhaust velocity, that is, the speed at which the propellant is expelled. However, they expel a large amount of propellant. In a short period of time, they burn through a huge amount of fuel, creating powerful thrust, allowing us to launch rockets from Earth and send spacecraft into space. In electric engines like ion thrusters, the particles are expelled at a much greater speed, but there are fewer of them. As a result, the thrust is lower, so low in fact that it wouldn't be enough to lift a spacecraft off the ground, let alone carry it into space. That is why we still cannot do without chemical engines. However, electric drives have a much higher specific impulse, a parameter that essentially describes how efficiently an engine operates. With the same amount of fuel, once in space, an ion drive will accelerate a spacecraft much more efficiently. It will just take longer to do so. And why am I saying all this? Potentially, antimatter engines could have the highest specific impulse, even among other technologies that still don't fully exist. The specific impulse of antimatter engines could be up to several thousand times greater than that of conventional chemical rockets. It would be higher than electric drives and even the promising nuclear ones, both fission and fusion. The exhaust velocity of some types of antimatter drives could be not much less than the speed of light. In general, the matter-antimatter pair as an energy source has the highest energy density. It is 300 times higher than fusion reactions, 1000 times higher than fission reactions, and about 10 billion times higher than regular chemical reactions. With a small amount of fuel, you can generate an immense amount of energy, which is crucial for long-distance space travel. It is the key to making deep space exploration a reality. And if you look at this graph from the NASA's presentation, antimatter drives are the closest to the goal in terms of maximum efficiency. The real question is how easy it will be to reach this goal in practice. It is likely that many of you know that today it is believed that regular particles have companions, antiparticles. A particle and its antiparticle are very similar. They usually have almost all the same parameters, but one of them differs. A typical example is the pair of an electron and its antiparticle, the positron. They differ in charge. The electron has a negative charge, while the positron has positive charge. And in the pair of a neutron and antineutron, the difference lies in the magnetic moment. But the most important property which interests us today is the fact that when a particle and its corresponding antiparticle meet, annihilation occurs. This releases a tremendous amount of energy. That's why it is said that annihilation of matter or antimatter pairs has the highest energy density. Another advantage is that this reaction is spontaneous. If we talk about other types of engines proposed today, such as nuclear ones, special conditions need to be created for the reactions to begin. This is especially true when it comes to using fusion reactions. In the case of matter-antimatter, there is no need for super complex reactors. Unlike with nuclear reactions, which require extreme pressure and temperature conditions to initiate and maintain the reaction. It sounds like we're just taking a bunch of matter and a bunch of antimatter. In short, we collide matter and antimatter and off we go. But of course, it's not that simple. There are different types of reactions involving antimatter, and the situation changes depending on which particles are being collided. Additionally, there are several ideas about how exactly to use antimatter. Among the potential applications, there are several main schemes. First, direct use of products of the reaction. This means we initiate annihilation and then directly use the resulting energy to create thrust. Next, we can use the energy obtained from annihilation to accelerate some propellant from regular matter. The thrust then would be generated by that propellant. Another way to use the energy from annihilation is to power the spacecraft systems, essentially generating electricity. And there are hybrid options where matter-antimatter reactions could be used to trigger nuclear reactions, either fission or fusion. Each of the mentioned schemes also has its own subtypes. As for possible reactions, it seems that, quote-unquote, the simplest option would be to take an electron and an anti-electron, that is a positron, and collide them. When two such particles collide at low speeds, both particles annihilate, and as a result, two gamma photons are produced. You could say that all the mass was converted into energy. But here lies the problem. How do we direct this energy into a useful form? What do we do with this gamma radiation? Here we can recall photon drives where the momentum of light is used in one way or another. Even though photons don't have mass, they do carry momentum, meaning they can generate thrust. I've already used the example that even a flashlight emitting photons from one side creates thrust. Very, very weak thrust, but it does create some. Or photons can transfer momentum to a sail. In general, we need to create some kind of asymmetry, so that the radiation goes in one direction, and then thrust can be generated. And with gamma radiation, such high energies are produced during the annihilation of matter and antimatter that it's problematic to achieve this. To create thrust, this radiation needs to be focused and directed in a specific direction. You can just take a regular mirror and redirect gamma radiation with it. These photons would simply pass through it. This paper states that in order to create a mirror capable of redirecting gamma rays with an energy of 500 keV, it must have a density comparable to that of a white dwarf. If we don't try to directly use photons to create thrust, but instead use them to heat and accelerate another propellant, then again, such high energy photons will not interact effectively with the material passing through it. And I haven't even mentioned that if there are people on such a spacecraft, it would be a good idea to protect them from all this gamma radiation. So strong shielding would be needed as well. In general, electron-positron reactions are not really considered for practical use. There is a more interesting option, that is annihilation of proton-antiproton pairs. If the reaction of an electron and positron looks like this, then with proton and antiproton it looks like that. Among the products of annihilation we have pions, positively and negatively charged, as well as neutral ones. These pions decay, but they can still be used to generate thrust. The charged pions can be captured and directed in the desired direction, which will generate thrust. They even travel at speeds up to 94% of the speed of light, which is great for propulsion. However, there are some drawbacks to this approach. As I mentioned, we can use the charged pions to create thrust from the reaction products. However, as you might guess, this is not all the available energy. So, not all of the mass of the initial proton-antiproton pair is converted into useful energy. In the best case, 64% is converted, which is actually still quite good. Another significant problem is the gamma radiation. We were just talking about pions, but a keen observer would notice in this diagram that even further, we can't avoid gamma photons. All the pions decay, and they decay very quickly. But the charged pions that we want to use for thrust manage to travel 21 meters before they decay. Their decay products, muons, travel almost 2 kilometers. But the neutral pions decay almost instantly. They manage to travel only 0.06 micrometers before decaying into gamma photons, which have an energy much higher than those from electron-positron annihilation, a whole 200 mega-electron volts. In general, we have the physical possibility to direct a significant portion of the energy obtained from annihilation towards propelling the spacecraft. However, a very powerful radiation shield is still required. The second approach is to heat an intermediate substance and use it as a propellant. There are also several options here. The first is the so-called solid core engines. Here, the products of proton-antiproton annihilation hit a specific part made of metal with a high melting point. For example, it could be a piece of tungsten. The piece heats up, and the propellant is passed through it, which is then ejected through the nozzle, creating thrust. In this case, up to 90% of the annihilation energy is transferred to the tungsten block. However, there are still limitations in the form of temperature. The specific impulse here is higher than that of chemical rockets, but not extraordinary. Overall, such an engine is comparable in efficiency to nuclear rocket engines. Another option is a gas core engine. Here, instead of a solid block, there is gas at high temperature. This engine can handle higher temperatures, but a significantly smaller portion of the annihilation energy is used, up to 35%. The next step is engines with a plasma core. Here, it's not just gas, but plasma, meaning that gas is ionized. These engines show very high specific impulse, but only about 10% of the energy produced is utilized. Quite interesting options are hybrid antimatter engines. The examples I mentioned earlier require large amounts of antimatter. In some cases, very high. But this is perhaps the main issue with antimatter engines: obtaining the necessary amount of antimatter. We'll talk about this in a bit more detail later. Hybrid engines try to at least partially solve this problem by reducing the required amount of antimatter from the system design perspective. One such concept was developed at the University of Pennsylvania and is called the ACMF drive. This stands for Antimatter Catalyzed Micro Fission Fusion Drive. It's an engine that uses microscale fission and fusion reactions catalyzed by antimatter. The fuel capsule containing deuterium, tritium, and uranium-238 is launched into the reactor chamber, where it is first irradiated by ions and then hit by a beam of antiprotons. Upon interaction with antiprotons, part of the material in the capsule annihilates, releasing enough energy to initiate the fission of uranium-238. This in turn triggers a fusion reactions between deuterium and tritium. The products of all these reactions in the form of plasma and radiation are expelled, generating thrust. The advantage of such a system is that each stage here is simplified compared to using these technologies separately. In this case, only a relatively small amount of antimatter is needed. For example, to travel within the solar system and reach Pluto, only about 100 grams of antimatter would be required. In today's reality, though, only is definitely an understatement. However, it is still incomparable to the amount of antimatter required for direct thrust generation. The decay reactions are minimal here, which reduces radioactive emissions, and there is no need to build complex reactors to sustain fusion reactions as they occur briefly. We launch one capsule, irradiate it with antimatter, boom, and off we go. Then the next capsule and so on. This concept is reminiscent of a nuclear pulse propulsion engine like the Orion project, where nuclear bombs are continuously ejected behind the spacecraft. When they explode, they propel the vehicle forward. Such a hybrid engine could potentially offer both high thrust and high specific impulse. In the same University of Pennsylvania, a concept for an interplanetary spacecraft was developed that would use the ACMF engine. The project is called ICAN-2. Here we have a spacecraft with an engine, shock absorbers like those used in nuclear pulse ships. Here we have command modules and necessary radiation protection from the engine operation. Some papers suggest that such a spacecraft could realistically be built within a couple of decades. It would be used for travel within the solar system, and it could reduce the journey to Mars and back to just 120 days, including a month-long stay on Mars. A trip to Jupiter and back could be completed in 18 months, with 3 months spent at the system of Jupiter, and a trip to Pluto could be completed in just 3 years. In general, this is much faster than current options. Another concept of a hybrid engine, the AIM-STAR, is similar to the previous one in that it also initiates a fission reaction followed by fusion, but the mechanism itself is different. Here, antiprotons are contained in a special trap, and small droplets of a mixture deuterium-tritium or deuterium-helium-3 with small concentrations of uranium-238 or lead-208 are injected into it. Such engine could be more powerful, but it also requires more antimatter. Another interesting option is antimatter sails, but it's not about using gamma radiation for propulsion. Here, thrust is generated through fission reactions. The sail is made of 2 layers. The outer layer is made of carbon fiber, and the inner layer is made of uranium-238. Then the uranium is irradiated with antimatter, triggering fission reactions. The reaction products are expelled, generating thrust. We can't just go and build a full-fledged antimatter spaceship right now. There are a number of problems. Some are technological, we need materials that can withstand high temperatures, or we have to limit the temperatures, as well as effective shielding from gamma radiation, which significantly increases the spacecraft's mass. But in principle, all of this is solvable. The main problem with the idea of using antimatter for space propulsion is the lack of sufficient antimatter. It involves the problem of production and the problem of storage. Of course, things are not as grim here as with warp drives, which in many variants require negative mass, something we basically have no idea how to obtain. With antimatter, it's a bit simpler, it exists. Antimatter particles regularly arrive from space, they're also produced in thunderstorms. We now routinely produce them in particle accelerators. In fact, you're producing it yourself right now. Our bodies contain small amounts of the radioactive isotope potassium-40, and when it decays, it releases a positron. So we're essentially our own antimatter factories, though very inefficient ones. Not only do we need to produce antiparticles, but we also need to store them somehow. As you might have guessed, we can't just put antimatter in a container and call it a day, because it, annihilates upon contact with matter. That's why we need special electromagnetic traps, such as panning traps. These can hold antimatter using magnetic fields, preferably in high vacuum and at low temperatures. The technology is slowly developing. At first, antimatter could only be held in a trap for a few minutes. Now, however, the time frame is measured in months and even years. There are even developments of portable traps that can move antimatter for study in other laboratories. Of course, such portable containers will be absolutely necessary for spacecraft. Such a trap is being developed at CERN. However, it's almost 2 meters long and weighs a ton, literally. So the plot from Dan Brown's Angels and Demons with a compact portable antimatter bomb is still pure science fiction. But most likely the traps will keep getting smaller and they will be able to hold more antimatter for longer periods. You may have heard that antimatter is called the most expensive substance on Earth. They say that 1 gram of antimatter costs hundreds, if not thousands of trillions of dollars. Of course, this doesn't mean that anyone is ready to buy antimatter at that price. The cost is calculated based on how much it would take to produce 1 gram of antimatter. However, it's a good indicator of just how difficult this is in practice. I mentioned that antimatter is now routinely produced in particle accelerators, specifically at Fermilab and at the Large Hadron Collider. And there has been some progress in production as well. Accelerators are capable of producing tens of millions of antiprotons per minute. It might sound impressive until we calculate that to produce just 1 gram of antimatter at this rate would take tens of billions of years. And as you may remember, even in one of the least costly engine designs, we would need 100 grams just to reach Pluto, let alone flights to other stars. But this does not rule out the idea of antimatter-powered engines. Neither the Large Hadron Collider nor the accelerator at Fermilab were specifically designed for the production of antimatter. If laboratories and equipment are specifically built for this purpose, and if the field develops, it's quite possible that a significant amount of antimatter could be produced in a more reasonable time frame. There are even clever ideas like the one in this paper where it is proposed to produce antimatter directly on a spacecraft using powerful electric fields that create particle-antiparticle pairs, which could then be used on site for propulsion in space. This is still just theoretical, but it's not impossible in principle. As we can see, the concept of an antimatter drive is wide. An engine where antimatter is used directly to generate thrust for ambitious goals like accelerating to 50% of the speed of light to reach another star system in just a few years, with the ability to decelerate and so on, might require millions of tons of antimatter, according to some calculations. At the current production rate, it's not certain that the entire lifetime of the universe would be enough. So at the very least we'd need to increase this rate, or perhaps make goals less ambitious. Hybrid engines seem much more realistic. In one of the articles I used as a source, they provide the following historical analogy. In 1898, the first droplets of liquid hydrogen were obtained. Now we produce it by the hundreds of tons. Maybe in 100 years, a similar increase by many orders of magnitude will happen with antimatter. And again, this doesn't require searching for some mysterious substance with negative mass or fundamentally new principles. We are already doing it. We just need to do more and make it better. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, share the video with your friend, and subscribe for more videos in future. Bye.